the James Webb Space Telescope is the most powerful space telescope ever made. It is also the most complex space telescope designed yet. So how did the structural design for Webb come to be?
It all started back in 1988, 2 years before the Hubble Space Telescope was launched. The idea for Webb first occurred in a conference that was held to figure out what do we do after Hubble. So there was a conference held, astronomers came from around the country, and they brainstormed about what would Hubble not be able to find that would still be so exciting that we had to do it with a new telescope. There was a need for Webb because the Hubble Space Telescope can only see certain wavelengths, ultraviolet, visible light, and a little bit of infrared. And of course, you can't see everything with one telescope, so what's left to look at is longer wavelengths infrared and maybe even a bigger telescope. So we need that to be able to do three things. One is to look farther out into the distant universe because the receding galaxies have their light stretched out to become longer and longer wavelengths than what it was when it was sent out. We need infrared to be able to see inside glowing clouds of gas and dust where stars are being born today, because the dust obscures our view and the infrared light can go around the dust grains and let us see inside. And we need infrared to see things that are too cold to emit visible light, and there are a lot of them. For instance, when stars are being born, they're pretty chilly at first, and so they're just barely turning on as stars, but we can see them with infrared light. So all three reasons say, build us an infrared telescope, and you can't do this work from the ground because the atmosphere of the Earth obscures our view. So we needed an infrared telescope that would operate in outer space.
Before any designs for Webb could be created, certain criteria needed to be established first.
We had to figure out, well, number one, how big could it be? Number two, how cold could it be, or should it be, to achieve the scientific objectives? And number three, where to put it so that it could get that cold.
But we knew we wanted to have international partners on Webb, just like we did on Hubble. And those partners were the European Space Agency and the Canadian Space Agency. Now, we also knew that because this is a NASA-led mission, NASA wanted the bulk of the science and technology, and so we were going to be building the telescope and some of the science instruments. What had to be worked out was exactly which science instruments would be built by which people. Again, because it's a NASA mission, we knew we wanted the main camera that's going to return most of the science. And so there was a negotiation with what kind of technology and expertise could the European Space Agency bring, and similarly in Canada. And this was a negotiation that took several years before it was decided that ESA would build one of the spectrographs, and there would be a joint instrument that worked in the mid-infrared that was a combination of both ESA and the US. And then finally, Canada had built fine guidance sensors before, and so that was more or less their strength, and we wanted to capitalize on that, and that's what they're building for us as well. And so all this, I like to think of it almost as a dance, had to happen between these partners. They had to figure out how they wanted to move, and then once that instrument package was more or less decided upon, then you could say, okay, this is the box that my instruments have to fit in, and you can begin to work around the rest of the observatory then.
With the new criteria set, ideas for the telescope's structural design could begin to be drafted.
Early on, the study was led by Goddard, and folks from the Space Telescope Science Institute were involved in coming up with some initial designs. But we knew that to get further, we would have to bring in folks from industry who build large spacecraft and telescopes even. And so we had study, we announced there would be study money available and interested parties could apply. And so Ball Aerospace, TRW, and Lockheed Martin were all industry partners who said, you know, they had concepts that could work. And of course, the government had to have its own model, which we call the yardstick model, to make us smart buyers, because eventually you would have a contract go out for industry to make the telescope, but you had to know enough about your own designs to make sure that you could judge what others were proposing as their designs.
There were a lot of ideas in the pre-phase A when we were just starting out in 1995, 1996. The big question is, well, how are you going to fold up the telescope? You have a list of different ways you could fold a telescope. So different companies chose different ways to explore that. One idea is, well, how about we have more or less circular telescope, but it'll have a center octagon and pedals. Some of them fold up, some of them fold down, and then you could get that into the rocket. Another idea is, let's have a smaller telescope. Maybe we can't quite do this, but it will be simpler if you could make it smaller. And then you can have a fixed mirror and it's surrounded by the protective umbrella that it needs. Or another way, well, how about if you have the mirror separated into 3 groups and fold 2 groups around the third one. So that's another way to fold it up. And then we ran the bigger competition to do the Phase A study. So that's the one where TRW teamed up with Ball Aerospace to give us one idea, and Lockheed Martin gave us another idea. So both could have worked. Both were excellent engineering ideas, but we eventually, after a long discussion, we said, okay, TRW, you're the ones.
Even after the official design was selected, further modifications needed to be made to achieve Webb's final structural design.
If you look at like the earliest sort of real design of the telescope from an architecture standpoint, it's not a whole lot different than what we ended up flying in space today. So the only real change that was made was to the size and how we configured the primary mirror itself. So the original design actually had 36 individual mirror segments that made up the primary mirror. Now you notice what we actually ended up flying was just 18 segments. So that's a pretty big reduction. The other thing was the original design had us at 8.5 meters in diameter. Again, we ended up flying about 6.5 meters. A lot of those early design decisions were driven by mass, cost, and schedule. And what we realized early on was the 8.5 meter mirror was just going to be too heavy for our rocket, and the size of that mirror was just too big for the fairing to be folded up inside of. And also, another big part of it was manufacturing the beryllium segments, where you're dealing with 36 individual pieces to build. It was a lot easier and a little bit less time consuming to build just 18. So ultimately, those were the major changes to the primary mirror design. The sun shield was just a concept on a napkin early on. We actually had to get started on the telescope first, because we knew building that large beryllium mirror was going to take a long time. So it got out in front of the sun shield, and so the sun shield got started a little later. Once we had Northrop Grumman on board as NASA's partner, again, we've already started the design of the telescope. We got into the sun shield design, and we launched, really early packaging studies, and actually, everything from how big the sun shield needed to be, how we were going to build it and make it. But the most important thing was how many layers did this sun shield have to have in it. We looked at 2 layers, 5 layers, 7 layers. So that was like one of the big early questions that we answered with these early concept studies. What we used was computer simulations, where we actually built computer mathematic models of the thermal performance of what a sun shield layer would do. So we looked at everything from 2 layers all the way up to 7 layers, and via these computer simulations, the mathematical models told us that 5 layers was the right number and would do the trick. The sun shield basically has 2 primary jobs. The first is just to provide shading for the telescope, to keep it in darkness, to block the light of the sun. So as the telescope points all over the sky, we always wanted it to be in the shade from the sun. And that kind of determines the overall sort of size of the sun shield. The second more complicated thing that the sun shield has to do is it has to cool the telescope. And that is the reason why you have these multiple layers. So 1 layer doesn't cool the telescope. 2 layers, because you get more heat escape, it cools down a little bit more. Ultimately, it was all these computer simulations which told us it would needed to be 5 layers, which would provide the adequate cooling. So those are the 2 things that ultimately designed sort of the overall architecture of the sun shield. The third major element of Webb, the observatory, is the spacecraft bus itself. And early on in the development of Webb, we didn't put a big priority on getting started with the spacecraft bus. And that was generally due to the fact that NASA and industry had, we build spacecraft buses all the time. So we knew there was going to be some challenges with this spacecraft. However, we didn't quite know at the time how big those challenges were going to be. So anyway, the spacecraft was a little bit delayed while we focused most of our energy on the telescope and the sun shield design. Now, one of the main jobs of the spacecraft bus is to structurally support the telescope and all of the instrument during launch. And the spacecraft bus only weighs 1/3 of the total mass of the observatory. So it has to hold twice its own weight on top of it during launch. So that was a big structural design challenge for our engineers. The other challenge that kind of came out that kind of ended up being a bigger challenge than we originally thought was the thermal design of the bus. Again, because it's always pointed at the sun, it has this big hot sun shield on the other side of it. So it was kind of trapped between the sun and the sun shield. Really, really hot place to be. And we had a whole lot of equipment in there to get the heat out. So the structural design of the bus and the thermal design of the bus really were two challenges that we got a little bit of a late start on.
Due to the complexity of the structural design, engineers and scientists would face challenges in testing the telescope.
For testing Webb, we had to use a building block approach because we couldn't test the entire built-up observatory. It's just too large and just way too complicated to test the entire thing. So we used a building block approach where we tested small sub-assemblies, and then we brought those sub-assemblies to a next larger assembly, ultimately building up to the largest test we could do safely. But in the end, we just could not test the entire assembled observatory. And that's where this building block approach had its challenges. You lose the sort of system level interactions of the fully assembled spacecraft. And it's very late in the game at this point because it's just about a year before launch where we finally have a fully assembled observatory. And at this point, it's unclear how these system level interactions are going to go. And this is where those computer simulations really come into play. They augment all of our testing to sort of fill in the missing blanks or provide the missing puzzle pieces for those system interactions and all the things we can't quite test for on the ground. We rely heavily on these computer models, and that's what really gives us a lot of confidence. There's computer modeling, there's simulations, along with our pretty extensive test program, and that's what gives us the confidence that everything's going to work at launch.
After launch and the intricate deployment, Webb is operating remarkably well, capturing amazing views of the cosmos.